So good morning students. So today's topic that is very interesting and that is come in connection with the previous discussion, that is the hyperfine splitting of the EPS spectrum. So the first would like to take some very interesting and common example of EPS spectrum, and later we will discuss about some very critical and typical type of examples. So the first example that we would like to discuss is the hydrogen atom, and we know that in hydrogen atom there is one single electron is present, and in the nucleus only single protons is present. So definitely they will interact, because we know that both protons and electrons have the nuclear and the electronic spin quantum numbers, and both of them have the magnetic moment. So definitely they will interact and split the electronic signals. So hydrogen atom, it consists an unpaired electrons with s equal to half and a proton with nuclear spin number I equal to half. So both of them is half and half. Thus the ms, that is the spin magnetic moment, equal to have both orientation, both direction is plus half or minus half, and mi equal to plus half and minus half. So in the absence of magnetic field, when Bz equal to 0, the electron spin energy levels are degenerate, that is have the same energy, and application of Bz removes the degeneracy between them. Thus ms equal to minus half sublevel going down and ms equal to plus half sublevel going up. We're going to know that the energy equation E equal to Ge into mu b into Bz into ms. So if you put ms equal to minus half, the energy becomes negative, so it decreases, and when you put ms equal to plus half, its energy becomes higher, so it goes up. So minus half energy level goes down, and ms equal to plus half goes up. So each of these electron sublevels interact with the nucleus, giving 4 sublevels designated by the value of mi. Okay, so this is hyperfine interaction. Using the selection rule of 2 ESR line, using the selection rule means when this type of hyperfine splitting already performed or had taken place, then the selection rule is that the value of the delta mi should be 0. That means the transition takes place where delta mi value should be 0. So using the selection rule, 2 ESR lines, that is doublets, are observed as shown in the experimental spectrum. They are equally intense. The spacing between them gives the hyperfine coupling constant A, expressed in the units of Tesla or millitesla, and when it becomes small, it can express in Gauss unit also. So here is the diagram of this current species. So it's the hydrogen atom. So when Bz equal to 0, the two energy spin state energy level is same, that is ms equal to plus minus half. They have the same energy, that is degenerate. And when you apply the magnetic field when Bz not equal to 0, then the minus half states goes down and the plus half state goes up, and where ms equal to, this is called the spin splitting or fine splitting. Okay, so this is happening in the presence of the applied magnetic field, and also called the Zeeman splitting. And when there is a nuclei present just vicinity of the states, so this interact, that is mi also interact with ms and gives rise to the resultant spin. So at that time the energy level is guided by the ms, because the minus half states again interact with a plus half and gives rise to the energy minus. That's why it goes down, and when minus half interact with this minus half, it gives the higher energy, so it goes up. Similarly, this state contains plus half, so the minus half state of mi interact gives a negative energy and it goes down, and the plus half interact gives energy more and it goes up again. Now two possible transition. Keep in mind that delta mi value should be 0. So minus half to minus half is one possible transition, and plus half to plus half is another possible transition, and both of them, though it looks like it's the length of these energy levels is different, but it's not happen in the case, and they appear as the same intense peak. Okay, so this is the representative ESR spectrum or ESR spectra graph that is appeared as a derivative plot. So this is for one transition and this is for another transition, and these are the peak point for these two transition. Okay, now the next example is the methyl radical, where not only a single proton but a collection of 3 protons are present. it contains an unpaired electron with s equal to half and 3 equivalent proton. Sorry, just a moment.